So 1.4 has two main categories we're going to talk about. And the one is the different number categories. So the warm up has different numbers for you to fill in if you know the different categories and how to come up with them. But we're going to go over those in a second anyway. The second thing will be domain and range. So first, we're going to talk about what are the two number sets that we talk about, or different number sets, and how do you find and write domain and range. So here's all the different number sets that we're going to have. We're going to start at the very top. This top part here encompasses all numbers that you could possibly think of, and that's called the reals, or real numbers. So anything you possibly think of, like 2 and 4.7 and 6 over 11, anything you could possibly think of. And some other weird ones like the square root of 7, which is a long decimal. You could think of like 0.53, right? Maybe some repeating numbers there. That's what it means with the line above it. And then some other ones like the symbol pi. Any of those things could be representative of a real number. And then we're going to break it apart into two separate categories, taking all the numbers you could possibly think of. And one category is the rationals, the other one is the irrationals. So rationals is anything that can be written out as a fraction. I'll put that over here. Can be a fraction. Specifically like a whole number over a whole number. So if you see like 7 over 3, if that can be written as a fraction, which it is a fraction, then it can be a rational number. Something like 2.5 can be a fraction as well. You could say it's 2.5, right? Or it would be 5 over 2. Same thing, right? Even things like 0.3 repeating can also be written as a fraction, which is 1/3. And also this includes regular whole numbers as well, like it's like 8, 10, -2, -7, whatever. I do -10. So now we're breaking apart from the reals into the rationals and irrationals. Irrationals are numbers that go on forever. Go on forever. So it's a decimal, it never ends, and never repeats. At least in a pattern. So this one repeats. It's 0.3 repeating, but this one has a pattern to it, whereas irrationals don't. So for instance, pi is 3.14159 ... goes on forever. Other ones, weird ones, would be like the square root of 7, like I had up there. That's a long decimal. It's like 2.7, 2.8 something. But if you put it in the calculator, you get a really long decimal. Or you can just make one up on your own. If you said it was like 1.457 ... that kind of tells me that it's going on forever, but there's no pattern. So irrationals versus rationals, a lot harder to come up with irrational numbers, that's for sure. So we're breaking into those two categories. Then from there, we're going to break down the rationals into integers and non-integers. So integers, you can kind of think of them as your whole numbers and the negatives. So it's the -2, -1, 0, 1, 2, 3. We can put dots, ... on both sides. Non-integers would be the numbers in between. That would think of it as like your decimals. So like -4.5 and 3/2, like just things like that. Mostly decimals and fractions. 10 over 7. So you have non-integers, you have your integers, and then for there, we're going to break that down. We get even like more specific. Now we're going to talk about the negatives versus the positive integers. Well, this actually says non-negatives. The reason for that is when you talk about the negatives here, we're going to do like negative. Well, I'll do it this way: -1, -2, -3, -4, so on. This way, when they say non-negative, that means they can also include 0. So it's 0, 1, 2, 3, 4, and so on. then really that should be all the categories you should be aware of and know about. But these last two categories, all they do is they break apart the non-negatives into what they call natural or the counting numbers. So when you first start learning how to count on your fingers, you start with the number 1 and count up from there. So as you can tell, it's almost the exact same category as the one above it. The only number that leaves out is the number 0. So it is a category on its own, naturals and counting numbers, because when you say that, you're not including the number 0. Non-negatives, you are including 0. So if you're a part of any of these categories, you're also part of the category above it all the way through. So if you are the number 0, look at the number 0, you are part of the non-negative integers, you're part of the integers, you're a part of the rationals, and you're part of the reals. If you're an irrational number, you're only part of the irrationals and the reals. So you're a part of every category that's above it as you go up through the arrows. So obviously, if I give you a random number, it can belong to more than one category in one set. So let's try some. Identify each number as belonging to the set of integers. So integers, rationals, irrationals, or reals. So everything here can be posted as real. Excuse me. Real. And what else could they be posted as? Yep, so we could have integers here. Is this an integer? No. I don't think so. Integer, probably not. Integer, yes. I'm going to go through each category. Rational, well, if it could be written as a fraction, for instance, this could be written over 1, that would be rational. This is a fraction, rational. If you put that in the calculator, you get a really nasty decimal. This is not going to be a rational number. This one could be rational as well. Irrational numbers, well, anyone that you said rational to, they can't also be irrational. So the only one I think is irrational, if you put that in the calculator, is the square root of, or negative square root of 18. Irrational. And that would be all of them, right? We did integers, rational, irrational. So you can belong to more than one set. 2. Give an example of a rational number that's not an integer. Well, you could see that right above for one of these examples. But rational, I would just probably pick a fraction that cannot be reduced to an integer. So for instance, you can't pick like 6 over 3 because that can be reduced down to the number 2. So I won't use that. So, but we could do something like 14 over, let's say, 9. That would be rational, but not an integer. Give an example of a real number that is an integer and not positive. So let's think about negative integer. We could do something like negative 6. Anything is a real number, so you could pick whatever you want. Then you have to meet the restrictions of being an integer, but not positive. Give an example of a real number that's between 0 and 1. Well, again, a real number is anything, so just pick anything between 0 and 1. We could say like 0.3. Now we're going to switch directions and go to domain and range. And you probably have done this before, but domain is a set of all x values in a table, graph, or equation. When looking at a graph, you start and you read this actually from the left to the right. We only do this for graphs. We only do this for graphs with this new notation. You've probably seen this before too. This is called set builder notation. It has this x here. This stands for, the curly brackets is the set of all x such that, but you don't have to memorize this. What we really need to know is that we're going to put in numbers from here as we read the graph from left to right. So maybe it's something like, it goes from like 1 to like 7. It's always going to be a lower number on the left and a higher number on the right. The range is reading the y values. We go from the lowest to the highest. So this one Same idea. You have these less than or equal to signs in between. You go from the lowest number, say like -4, to the highest number, say 0. You're looking from bottom to top. The way you read this, which we will just show you how to read it, we don't have to really memorize this, is the set of all x. We'll do y since y is above it, such that -4 less than or equal to y is less than or equal to 0. So all those words are talking about the curly brackets and the y and the colon. Oh, okay, sorry, I'm back. So let's do some domain and ranges for these graphs. These ones all have starting and ending points, so it'll be easier to make them up. So I'm going to do this without doing the set notation. We're just going to do it with from one number to the next. So we're just going to use this piece of it. Domain, from the farthest left to the farthest right. So the farthest left point is the number 0. You're reading off the x-axis. So we're going to go from 0 to farthest right, which would be 4. Range is the lowest to the highest, so the lowest this goes down to is -1. Now we're using y. The highest it goes up to is 2 on the y-axis. Domain for b, the farthest left would be -2. Furthest right would also be a 2, but it's positive. Range is the lowest point, -3. To the highest point, I'm going to use y this time. Highest point is +3. So I'm going to do one more and then have you guys finish off the rest for D, E, and F. I talk about F a little bit. Then we only have a couple examples left. All right, C. The farthest left it goes is all the way over here. We don't care about how low it is. It's just how far over we went. 1, 2, 3, 4, 5, 6. From -6 all the way over to the right. 1, 2, it looks like 3. Less than or equal to 3. These will always be less than or equal to symbols if you go from the farthest left to the right and lowest to the top. If you flip these numbers around, you would then have to change the inequality. So the lowest number here, we're doing the range, would be -5. The highest number, just read up. The highest you go up to is this point, which would be +5. Now I'll have you guys try D and E. I'll skip those ones and try F. The reason I'm going to do F, though, is because if you can tell here, there is a open circle at the end, and that will change how you write out your inequality. The inequality with less than or equal to means that equals includes it. If there's an open circle, that means you do not include it and you put just less than. So for instance, the domain would be from -5, including -5, but when you go over to the right, it does not include 10, so I will put a no equal to sign on it. The range is from 1, 2, 3, -3. Includes -3 because there's a solid dot here. But the highest we go up to, 1, 2, is +3 and does not include it. So no less than or equal to. Got 2 more examples, 6 and 7, and then we'll be done. But I would say pause it and make sure you can get D and E correct yourself. Pause the video and do that. Okay, number 6. To find the domain and range of a table like this, it's super simple. The domain would be the x value. Now, in this case, we don't see an x, but because we're used to this notation here, where it's called function notation, where we have f of x, the x value is inside the parentheses, and that's the letter j, so that means this is your x values. And when you do it this way with a table, all you do is you do a little curly bracket, and you write it from least to greatest, from left to right here. And the least number would be -7, and just write them out. -7, 0, 6, 8, and 12. Range is the other row. Be -5. You don't have to write -5 twice. Just once is sufficient. 0, 3, 22. Lastly, to find out what g of 0 is, like we've done this before as well, you're going to look at 0 on the j track, right? This is j inside here. So I want you to find 0 on j on that row, and then read down, which would be the number -5. That's just checking to see if you can read the table. Last one, I think I got rid of these ones in the notes. Last one would be example 7. All right, so the graph at the right shows the relationship between the age of a grapefruit tree and the diameter of its trunk. Let A of D be the age of the grapefruit tree whose diameter is D inches. First, we're going to do estimate the range of the graph, do domain, and then we'll do a reading of estimate A of 10. You guys can go ahead and try that for a second. I'll be back in a second here. All right, so hopefully you can try that. Or if not, pause it and do it yourself. So the range of the graph, asking for range first, so we're using the y values. There's no open circles here, so we use the less than or equal to. The lowest it goes will have to be an estimate. Yeah, this will all be estimates. I guess I said estimate. The lowest it goes is probably, since this is a 5 up here, I'd say maybe 1. The highest it goes is not quite 25. Maybe it's, say, 24. Again, just an estimate, so you can just ballpark it as best you can. Domain would be the farthest left it goes. Let me see if I can erase this here. Again, it's going by 5s, so maybe this is like, I don't know, 2. Maybe that's 1, 2. I don't know. Let's try it. Let's just do 1 again. There was X for domain. And the farthest right we go over, I think, does hit this line here, which is 15. And lastly, maybe something new is reading this instead of off of a table, but off of a graph. Estimate A of 10 from the graph. Explain what this means. So 10 is going in for, look up here, it's going in for the letter D. So this is giving us the diameter of 10. So if we go to the trunk diameter, which is on the x-axis, and we go to 10, it's asking us to read where the graph is at when we go to 10 as a trunk diameter. So we go up, let's change colors too. This is the point where it meets the graph at 10, and we're just going to go ahead and try to read across on the y-axis where this is at. So maybe it's about exactly halfway between 20 and 15. So maybe it's like 17 and a half, maybe something like that. So maybe we'll say that if we were to find A of 10 is about equal to 17.5. What does this mean? I'll just say it out in words rather than actually writing it down. So this would mean that a trunk diameter of 10 inches, maybe I will write it down. It's just kind of hard to do on here. Trunk diameter of 10 inches would mean, what are we relating these to? The age of the tree. So the age of this tree, which is a grapefruit tree, would be about 17 and a half years old. The tree is about 17.5 years old. All right, and that is the lesson for 1.4. See if you can understand that and finish up the few problems I skipped. And that will be a wrap on this lesson.